Bueno, muy buenas tardes. Es para mí realmente un placer, un orgullo poder presentar hoy al profesor Saku Tsuneta, que nos va a hablar del Sol y su influencia en la Tierra. El profesor Tsuneta empezó en la Universidad de Tokio, fue luego profesor y en el Observatorio Astronómico Nacional. Ahí se conectó con el tema del Sol, se dedicó a la instrumentación de rayos X para intentar comprender qué ocurre en el Sol. Y ha estado involucrado en todas las misiones solares de Japón. También ha hecho experimentos en globo, ha hecho distintos cohetes de sondeo. Lo que ha intentado era comprender más sobre ese comportamiento del Sol, sobre todo lo que llamamos el Sol violento. ¿Por qué el Sol se comporta de esa manera? En base a comprender la magnetohidrodinámica, el comportamiento magnético del Sol, las erupciones solares, etc. Todo ese mundo que hace que el Sol, que por supuesto es nuestra estrella favorita, no porque no sea distinta, el Sol es una estrella bastante vulgar dentro de la galaxia, pero es favorita porque es la nuestra. Y es la que tenemos, la que nos ha permitido que tengamos una vida como la que tenemos. Y por tanto, pues todo el mundo piensa que el Sol es una maravilla. Ahora, también tiene problemas el Sol, y de eso nos va a hablar hoy. El Sol también nos da guerra en algunas cosas, y eso es lo que hace que sea importante, muy importante, comprender cómo funciona y cómo evoluciona nuestra estrella. Pero el profesor Saku Tsuneta no solo es un gran científico, también ha sido y es un gran gestor. Le picó con el tiempo algo que nos pasa a algunos, yo lo conocí hace ya años, en donde te das cuenta que hay que gestionar también la ciencia, que hay que conseguir los recursos, la estructura, el funcionamiento de toda la administración de la investigación. Y él se involucró en ello, es actualmente el director general de ISAS, del Instituto de Ciencias Espaciales y Astronáutica de Japón, y también es vicepresidente de JAXA, que es la Agencia de Exploración Espacial de Japón. Es decir, está muy involucrado en lo que es la gestión de nuevos proyectos, nuevas ideas, donde lo que estamos haciendo no es otra cosa que ayudar a las ideas creativas de la gente más joven que se puedan hacer realidad. Nuestro trabajo como gestores, y yo estoy ahora en la Agencia Espacial Europea, pero está en la agencia japonesa, es tratar de convertir los sueños de los buenos científicos en una realidad. Y en eso es en lo que hemos coincidido y donde hemos visto cómo se puede avanzar mucho. Él lo ha hecho, estuvimos también juntos en un comité científico, que es el Instituto de Astrofísica de Canarias, y cómo ahí se puede ayudar a esa cooperación que hay, no solo de Japón con Europa, sino también con España en particular. Creo que eso hace que el profesor Saku Tsuneta sea un excelente invitado para dar una conferencia en este ambiente y que estoy seguro que van a disfrutar de lo llamativo y lo interesante que es ver al Sol no como ese disco amarillo que vemos y que ahora nos está castigando malamente con el calor que hace aquí, y lo digo yo que soy de Córdoba, pero es que realmente el Sol no es eso que vemos. Cuando lo vemos en otras longitudes de onda, vemos que es realmente muy activo, que están ocurriendo montones de cosas y que tenemos que hacer lo imposible para comprender qué es lo que ocurre en el Sol, porque ahí está nuestro futuro. Muchas gracias y adelante, profesor. You're welcome to talk.
Thank you very much, Alvaro, for a very nice introduction. My name is Saku Tsuneta. I am an astronomer studying the sun with instruments that I have developed with my fellow students and colleagues. So far, I have been involved in development of 3 science missions, 2 small rocket experiments, and 2 balloon flights. I have thoroughly enjoyed observing the enigmatic sun over the past 30 years. And we have made a few major discoveries towards solving the sun's mysteries. So my talk today has two keywords, only two keywords. That is sunspot and magnetic field. I start with the spectacular images of the sun obtained with Japan's Hinode satellite, which means sunrise in Japanese, to show you what sunspot and the effect of the magnetic field looks like. Then I present the recent observations that indicates that the sun is about to run out of sunspot. And is this important for us rather than a mere astronomical fact? This is a question that I would like to address. I will talk about the two faces of a magnetic field, the positive side to protect life and the negative side to potentially destroy life and civilization. So the story to be presented here centers on a sunspot, literally dark spot on the sun that was discovered by Galileo Galilei around 1612. And JAXA, NASA, United Kingdom, and the European Space Agency, Hinode was built by those agencies, has been observing magnetic field on the surface of the sun with unprecedented resolution and sensitivity since its launch in 2006. The Optical Telescope, the main instrument of the mission, has a large primary mirror measuring 50 centimeters in diameter and is currently the world's largest space telescope for observing the sun. The impact of Hinode Optical Telescope on solar physics is comparable to that of the Hubble Space Telescope on optical astronomy. So Hinode was developed to address key issues in solar physics, namely, how is the magnetic field created? How is the corona heated? How do explosions, solar flares occur? How is the supersonic solar wind accelerated? So I have been involved in the development of the Hinode for about 10 years, from its initial concept study to the launch pad. Scientists and engineers from the United States and the European countries also participate in their development and operation. So Hinode has discovered waves, ubiquitous jets, new kinds of magnetic field, a strong magnetic field in obscured solar polar regions, and enigmatic fine-scale flows in the prominence, the tongues of flame erupting from the sun's surface, among other discoveries. So I will show these fascinating activities on the surface of the sun with movies taken with Hinode. Here we see the sun as a telescope zooms closer and closer to its surface. As we draw closer to the sun, we begin to see these convection cells filling the solar surface. Nuclear energy in the core of the sun is transported through the convection to near the surface. Hot regions of the plasma, which are seen as bright patches, carry heat to surface and are cooled down by emitting radiation. The cooled plasma is seen as a dark rain and sinks deeper into the sun to be heated once again. So sunspots are dark simply because they are slightly cooler than their surroundings, since magnetic field hinders the convection motion that carries heat. This movie shows how the sunspot is finally disintegrated due to the attacking convection cells from the outside. So a sunspot has a magnetic field and appears as a pair. These two sunspots correspond to plus and minus polarities. So magnetic field lines are delineated in the X-ray image on the right-hand side. And magnetic field lines cannot be easily seen and do not smell, but they are real and carry energy, playing important roles in the universe. Magnetic field lines can be visualized using iron sand, for instance. The sunspot magnetic field strength is 1,000 to 3,000 Gauss. By contrast, the magnetic field strength inside the sun is about 100,000 Gauss, quite large. The Earth also has a magnetic field, 0.5 Gauss. The Milky Way has 1 millionth of Gauss, quite small. The sun has a very strong magnetic field compared with the planets and the galaxy. And the mechanism to produce a strong magnetic field is not yet understood. This is one of the important unresolved problems in astrophysics. Rotation of the sun combined with the convection, which I saw in the previous movie, are known to be two key ingredients to produce strong magnetic field. So kinetic energy, the energy of motion within the sun, is converted to magnetic energy through a process called the dynamo, working inside the sun. And the magnetic energy is then used to heat the corona. So this is not a visible image of the sun. It is a magnetic map. So the black dot indicates the negative polarity, and white dots are positive polarity. So you can see that the magnetic fields that come from inside the sun, forming a big plus and minus polarity region, a sunspot pair. Let me see once again. Yes, the plus and minus polarity are coming from inside the sun, forming a white big spot and a black big spot. That is a pair of the sunspot. So the color in this movie is a false color. The sun does not look blue. It is a color put by graduate students. So this is a photosphere, and we can see a big sunspot and surrounding convection cell near the solar edge. The curvature of the edge indicates the size of the image. By changing the filter on the space telescope, we begin to see chromosphere, a layer above the photosphere. The chromosphere was regarded as a dull thin layer in between the photosphere and hot corona in textbooks. But a fountain of jet and heating are ubiquitously seen, and these dynamic phenomena are due to the energy of a magnetic field. The sun is covered with such a dynamic phenomena. It's really beautiful. Whereas the optical telescope observes the sun's surface, the X-ray telescope aboard Hinode captures images of the corona and high temperature flares that range from between several million to several tens millions of degrees. The area around the sunspot where the strong magnetic field exists further illuminate X-rays. You can see the bright region in X-rays, and below that we have a sunspot that carries magnetic energy. It is fascinating that a solitary star, like the sun, emits intense X-rays from the corona. The heating of the corona with all the sporadic explosions from X-class big flares to tiny bursts, as you can see here everywhere, is driven by utilizing the energy of intense magnetic fields. The source of the energy for the sun is in the nuclear fusion reaction that takes place at its core. The temperature drops as we approach to the surface, where the temperature measures about 6,000 Kelvin. So the surface of the sun, the temperature of that is just 6,000 Kelvin. Mysteriously, the temperature starts rising again above the surface, and the temperature of the corona is exceptionally high at several millions of degrees. What you are looking at is a high temperature corona emitting X-rays. It is as if water were boiling fiercely in a kettle placed on a fireless stove, as inconceivable as it may sound. The phenomena is referred to as a coronal heating problem. And it is one of the major astronomical mysteries that something of a lower temperature is able to heat something of a higher temperature. This is against the second law of thermodynamics. So when I started my graduate course some 40 years ago, I was determined to solve this problem theoretically. In 1 year of effort, I gave up, completely changing my research topics from theory to instrumentation and observation by building instruments. I think that this was a very wise decision on my part, since the problem has not still been solved even now. A prominence, this horizontal feature located above the surface of the sun, is a cold material embedded in the corona. Since it is heavy and dense, it should have instantly collapsed due to the very strong gravitational force of the sun. It is, however, sustained in the corona due to the magnetic force, which overwhelms the gravity force. Let me proceed to the next section. The polar region of the sun is very important to predict the future of the solar activity, as I will explain later. This has not been done before Hinode. Hinode, for the first time, obtained a clear view of the solar polar region. When we read a book, we see the book face on this way, of course. No one reads the book from a highly oblique angle like this way. I think this figure shows the sun's rotation angle is 7 degrees tilted. And the Hinode high-resolution telescope obtained a crystal clear image of the polar magnetic field. The polar observation of the sun by Hinode is like a very oblique 7-degree reading of a book page. So let me summarize what we know about the polar region. When we see the sun far away, the sun's magnetic field resembles a bar magnet with each end of plus and minus polarities. This polarity reverses every 11 years, though we don't know exactly why this occurs. The Earth's magnetic field is much more stable, so that we can use the compass to know the direction. But this is not possible in the sun because the magnetic field is changing every 11 years. So this is the magnetic field distribution at the polar region as we see from above the pole. We have a coordinate transformation. You may see the many small patches, and these correspond to small sunspots. The blue color indicates the plus polarity, and the orange color indicates the minus polarity. We discovered that the polar region of the sun is covered with many, many tiny sunspots. In summary, this observation tells that when there is a maximum number of sunspots, the polar fields are thought to flip together, as shown in the left-hand side, so that in this particular case, in the year of 2008, South Pole has a plus polarity, North Pole has a minus polarity. So this is the usual sun. But Hinode found that the North Pole reversed its polarity first, producing a quadrupole structure. Namely, both North Pole and South Pole has a plus polarity. Let me explain the significance of this observation a little bit later. How anomalous is the sun now? This is the topics to be discussed in this section. The Galileo Galilei built a telescope and discovered the sunspot. His letter, written in 1612, shows a beautiful sketch of the sunspot, as shown on the left-hand side. 400 years later, the same technique, handwriting, is used in the National Astronomical Observatory of Japan, just to guarantee the uniformity of the record over 400 years. Similar observations have been done in many observatories all over the world. The uniform data bring us a critically important fact about the magnetic cycle of the sun. It is true that our new knowledge of the mystery of the sun is obtained through state-of-the-art satellite observation like Hinode, but it is also true that the simple but accurate records on the position of the sunspot by dedicated observers, generation after generation, also provides us a critical new finding. So the number of sunspots increases and decreases with an 11-year period as a result of the internal dynamo action. And the horizontal axis is the, I think, year, and the vertical axis is the number of sunspots. Between 1645 and 1715, you can recognize very huge sunspots were observed for 70 years. This is called the Maunder minimum, after the name of the Maunder who found this phenomena. So there is a record of global cooling during this period. Solar activity, as represented by the sunspot cycle, is somehow affecting the Earth's climate, perhaps in a significant way. So this is the number of sunspots as a function of time, starting from 1995 up to 2013. The red line shows the most recent sunspot number obtained at the National Astronomical Observatory with Japan. The number of sunspots start to increase around 96, reaching the peak around 2001, and reaching the minimum around 2009. So this is shown by red line. The black lines delineate the past 6 cycles with the preceding minimum as the same starting point. It's overlaid. These black lines show a more or less similar tendency, namely similar peak time and similar subsequent minimum time. However, the red line, as you recognize, the most recent cycle shows the considerable deviation. The solar cycle period reached 12.6 years instead of 11 years. This is a number of sunspots in the past 3 cycles. Horizontal axis is year, vertical axis is the number of sunspots. We can obtain the cycle period by measuring the time between minimum and minimum, or between maximum and maximum. In either case, the period becomes longer and longer, exceeding 13 years. So do we have a similar long period if we go back in time? We have to go back to around 1790. At the time, the period became 13 years, followed by a very low sunspot number period called the Dalton minimum. Solar magnetic field expands into interplanetary space, and it seals the Earth from cosmic rays, which are high-energy particles coming from beyond our solar system. When the sun is active, the amount of cosmic rays reaching the sun decreases, and vice versa. The shielding effect is very effective when the solar magnetic field is strong. So a proton collides with the atmospheric atoms. A proton coming from space entering the atmosphere collides with the atmospheric atoms, generating neutrons. The neutron collides with the nitride nucleus, generating carbon-14. So usual carbon is a carbon-12, has 6 protons and 6 neutrons, and its atomic number is 12, while carbon-14 has 6 protons and 8 neutrons, and its atomic number is 14 instead of 12. It is the same carbon, and they are captured in carbon cycle as a carbon-14 dioxide. So carbon-14 dioxide are recorded in 2 readings by photosynthesis process. Since the mass of the carbon-14 is heavier than that of carbon-12, the amount of carbon-14 in the 2 readings can be measured. So recently, astronomers are not looking at telescope. They are analyzing 2 readings. In summary, higher solar activity results in the decrease of cosmic rays entering the atmosphere. Decrease in the carbon-14 in the atmosphere results in a decrease in the carbon-14 recorded in 2 readings. So this horizontal axis is again the year, from year of 800 to the year of 2000. The vertical axis is the amount of carbon-14 recorded in 2 readings. If you have a higher carbon-14, that means a lower solar activity because more cosmic rays, while lower carbon-14 means a higher solar activity because there are higher solar activity because of a less number of cosmic rays. I was confused. We should not be confused. So the ancient sunspot number, as reconstructed by different researchers, is consistent with one another, as represented by different color. We see a remarkable trend. First of all, we recognize up and down. The solar activity is changing depending on time. We see a remarkable trend that as the cycle period is longer, the activity is consistently lower in the past few grand maxima and minima. This indicates that a simple measurement of the current cycle period can predict whether the sunspot number will increase or decrease subsequently in the future. How do we predict solar activity? The magnetic field strength inside the sun is tens of billions times larger than that found in the interplanetary space. These intense magnetic fields are created inside the sun by dynamo, as I mentioned. Let me try to explain how this happens. So this is the most difficult part in my talk. Even if you don't understand this, subsequent section is easier to understand. So let me explain. This is difficult. So magnetic lines of force are similar to rubber band. It's a rubber band. Magnetic field lines are twisted by the differential rotation of the sun, where the equatorial region rotates faster than the polar region. So rubber band magnetic field is amplified. The amplified magnetic lines of force then rise to the surface of the sun, release energy at higher altitude, creates a phenomena where the corona is heated and explosion occur. So it is similar to twisting the rubber band on a model aircraft and release it in the air. So you don't need to look into the details, but magnetic field strength in the polar region of the sun steadily weakens as a function of time from 1980s to the 2015. As a result, sunspot number is in successive cycles is systematically smaller than the cycle before. So the cause is the polar magnetic field, and the result is a sunspot number. The sun's current condition is, as I explained, is anomalous in three different ways. First of all, sunspot number has decreased systematically in the past three cycles. Second, its period is longer than ever. And third, its magnetic symmetry has been lost even temporarily. Since a similar peculiarity has happened before and around the times of the Maunder minimum and Dalton minimum, researchers studying the sun speculate that we will enter a Maunder minimum in 10-20 years. Nowadays, astronomers study tree rings and ice cores, as I said, to know sunspot number during ancient times. Measuring the captured carbon-14 in tree rings and beryllium-10 in ice cores can infer the number of sunspots in the pre-telescopic era. This has been very successful, and the sunspot number up to 10,000 years ago has been reconstructed, as shown here. We do not have the resolution to resolve the 11-year solar cycle. Instead, we clearly see many grand maxima and grand minima. So Maunder minimum-like events have occurred more than a few times in the past 10,000 years, as shown by blue lines. For instance, we noticed the Spura minimum that occurred between 1416 and 1550, a 90-year-old span of low solar activity. So such events are associated with the decrease in oceanic temperature. The latest grand maxima, which is here, started in the mid-20th century and ended with the start of the new century, is the largest one in the past 10,000 years. Let's try to predict the future of solar activity in a very, very crude way. As we have seen, the solar cycle period becomes significantly longer. If we compare the latest two cycles, yes, and the peak in the sunspot number decreases constantly. So if we simply extrapolate this, the sunspot number in the next solar maximum, if any, the year of 2025 is very small and is comparable to the Dalton minimum. I should stress that the opposite may happen. And this is a very reason to continuously monitor the polar region of the sun with the spacecraft. So astrophysics is concerned with our understanding of the universe, of course. It is usually nothing to do with our environment on Earth and civilization. The study of the sun is one exception. Recent studies clearly show that variations in the sun, such as those we learned today, have societal effects. The question may be how significant and serious is this effect. We'll see this in this section. In February 2015, UK Met Office made a surprising announcement that in the last 15 years, global surface warming has slowed despite increase in greenhouse gas emissions. This is not consistent with the many predictions which are shown by the gray line. The red line is a real observation. The gray line is a result of the numerical simulations. These predictions have not taken into account the possible effect from the sun. I mentioned that the Maunder minimum coincide in time with cold period. The Professor Aono in Osaka University developed a very unique method to use the flowering period of cherry blossoms to know the sunspot number in the pre-telescopic era. So temperature determines when the cherry trees flower. Hotter weather leads to earlier flowering, and vice versa. Using 822 years of historical record on cherry blossoms, viewing parties, etc., past 1,200 years of temperature in Kyoto, Japan, in March were reconstructed. Data taken between 1911 and 1940 was used to calibrate this methodology, confirming a remarkable prediction accuracy of 0.1 degree. Kyoto, Japan was the capital of Japan from 794 to 1868 for a very long time. And apparently, cherry tree flowering, viewing parties, episodes such as gift of the cherry flowers to the emperor were major events to the celebrities at that time, such as emperors, aristocrats, politicians, monks, and wealthy merchants. These events were depicted in diaries, chronicles, and poems. So this particular sentence reads that the emperor viewed and enjoyed the cherry blossoms in his private palace. And the emperor poured sake, a Japanese wine, for me. So this is a diary written by someone on April 14, 1644. So an issue associated with the carbon-14 found in two readings and the beryllium-10 in ice core, the problem of that method is dating to identify the year of each sample. Accuracy of dating is always an issue with these methods. As an advantage of this cherry method is that the ancient document that depict full flowering is extremely accurate. No need to interpret or extrapolate. So this is an important chart, the horizontal axis against the year from 800 to year of 2000. The top one is a reconstructed sunspot number. So sunspot number increases and decreases as a function of year. Bottom line shows the reconstructed of temperature of Kyoto from the year of 800 to the year of 2000. We notice a rather big change in temperature in Kyoto during the past 1,000 years. The error bar is also always important in science, as indicated by two red lines, increases, in other words, accuracy decreases as we go back to through the years. So we clearly see the signature of global warming. On the right side, you recognize that the temperature begins to increase near the year of 2000. But if we remove the heat island effect, which is that a big city like modern Kyoto has higher temperature than the surrounding rural area due to the concentrated heat source of the metropolitan city, the modern increase of the temperature is moderate, as indicated by the green line on the right-hand side. With this compensation of the heat island effect, we notice that the 10th century is warmer than now, a bit. So we see a Wolf minimum, Spoorer minimum, Maunder minimum, and Dalton minimum in the reconstructed sunspot number in the top line. And occasional low temperature period remarkably coincide with this low solar activity period, as indicated by arrow. We always see a dip in temperature associated with the lower sunspot number. Such a temperature decreases appear to occur close to end of the solar minimum with a delay of a few tens of years. So because the accurate dating and the high calibration accuracy, we conclude that there is a very high correlation between the winter temperature in Kyoto and the sunspot number over the past 1,000 years. We don't know why. Incidentally, during the mountain minimum, the Thames was covered with ice. London was really cold during that time. So at least 2 points on this globe, the temperature were lower during the mountain minimum. Do we generalize this to global temperatures? And similar correlation between the ground minimum in solar activity and the climate in Europe was reported by Dr. Usoskin, a Finnish scientist. Sunspot number and cold, wet condition in Europe over past 6,500 years were compared. He found 14 cold spells and 15 ground minimum in sunspot number, with 12 coinciding. So the extensive research by Professor Aono clearly shows that during ground minimum, the temperature in Kyoto were at least 2 degrees lower than the current temperature after removing the effect of the heat island. So if another mountain minimum happens, a similar temperature decrease would be expected. And this overwhelms the global warming effect, as you can see this figure. Are we ready to cope with various societal effects associated with this possible decrease in temperature? Then I change the topic slightly, namely, how do planetary magnetic field protect life and civilization? Needless to say, without the sun, it is impossible for the Earth to harbor its present life-friendly environment. This is unfortunately not the case for our nearby planets, Mars and Venus. Why does the only Earth have rich forms of life, including us? This is one of the fundamental questions that the 21st century astronomy and biology together should address and answer. The sun almost continuously ejects a huge amount of mass. So this is an observation made by NASA's stereo satellites. And the sun emits the mass and shock waves in addition to the usual supersonic solar wind, which collide with the Earth. But Earth is protected from this bombardment with the Earth's magnetosphere. I mentioned that the Earth has a very small magnetic field of 0.5 Gauss. This is quite effective to protect the Earth from the bombardment coming from the sun. Nevertheless, our modern technological civilization occasionally suffer during solar flares. For instance, GPS malfunction, disruption of our electrical power system, damage to meteorological and communication satellites, and radiation hazard to astronauts. Some planets have a strong magnetic field. Earth has a rather strong magnetic field, while others do not have any magnetic field. This difference is related to whether their internal planetary dynamo works or not. Among rocky planets, Venus, Mars, Mercury, Venus and Mars do not have a magnetic field, while Mercury has a magnetic field much, much weaker than the Earth. So if a planet has a magnetosphere to protect, to shield the planet against the solar perturbation, it will very effectively shield the planet from that violent interplanetary space. But if without such shield, like the situation of Venus and Mars, the surface of the planet suffers from this violence directly. This is clearly seen in the following simulation of Mars. So this is not a real observation, this is a simulation. Among 3 planets, only the Earth possesses inherent magnetic fields, as I mentioned. Do the magnetic field of the Earth protect the atmosphere and water from violent mass ejection due to the sun that may have stripped away the ancient Martian atmosphere, as shown here? We believe that the early Mars had atmosphere and liquid water. Mars is smaller than the Earth, and its weak gravity struggles to hold the Martian atmosphere. Early Mars had magnetic field, but Mars lost its own magnetic field in ancient times. The young sun was much more active than the sun now, emitting intense ultraviolet light, X-rays, and powerful wind. The initial rich Martian atmosphere and water may be lost due to intense solar storms, as shown by this simulation. So Earth was very fortunately has magnetic field so that we are able to be here today. While Mars does not have any magnetic field to protect its initial atmosphere and water. As a result, Mars is currently a no man's land, though it is located in the habitable zone. Habitable zone refers to the location of a planet orbit, where the planet is not so close to the central star, so that the water is not vaporized, and the planet is not so too far away, so that the water is not frozen. And what would happen if the humans are outside our magnetosphere to protect the planet and ourselves? The Apollo moon mission traveled beyond the Earth's magnetosphere, and Apollo astronaut showed a greater risk of the sort of a blood vessel disease called CVD. And CVD mortality among Apollo astronauts was almost 5 times that of non-flight and low Earth orbit. This strongly suggests that the Earth's magnetosphere protects humans. So do exoplanets have a life? There are 100 billion stars in our galaxy and 100 billion galaxies in the universe. In total, we have many stars, 19 zeros. The big question in space science today include how did life emerge on Earth? Does a second Earth exist? Do extraterrestrial life form exist? What is dark matter and dark energy? How did this universe begin and form? Among 5 questions, 3 are related to life on Earth and on other planets. So 20 years ago, we thought that our planet was alone. But now, we know that we are no longer alone, like this. Number of Earth-sized planets discovered dramatically increased in the past 10 years, so that we are not alone, probably. The fraction of stars with a planet is incredibly large. More than half of the stars in this universe likely carry at least one planet. Furthermore, 70% of those exoplanets are Earth-like in size. This number may change every day. So Venus, Earth, Mars are close to or in our habitable zone. Only the Earth is habitable now. I pointed out that the Earth's magnetic field may contribute to the emergence of life on Earth, but not on other 2 planets, Venus and Mars. Likewise, a planet called Kepler-22b is known to be located in the habitable zone. We do not know yet if the planet has magnetic field or atmosphere to protect this Kepler-22b. So assume that if you are on a planet around a distant star located in another part of the galaxy, and if you observe the 2nd through 4th planet of our own system, namely Venus, Earth, and Mars, what do you conclude about whether these planets have a life or not? The spectra from the innermost and outermost planet in the habitable zone show only carbon dioxide, that are Venus and Mars. Only the 3rd planet shows water, ozone, carbon dioxide, which are called biomarkers, indicative of life form. So the species on the distant planet observing us might guess that only the third planet of the solar system may have a life form because of these biomarkers. They are right. Indeed, this is what astrophysicists try to do for exoplanet with large planned missions such as NASA's WFIRST or ESA JAXA Spica missions. So then I proceed to a different topic. How do super flares affect life and civilization on Earth and other planets? So far, we have seen the positive side of magnetic field to protect the Earth, protect our civilization by the magnetic field carried by the planet. There is indeed a negative effect of the magnetic field, which I will explain here. So this section will address how a really big solar flare affects life and civilization on Earth and other planets. Solar flares are explosions that take place on the surface of the sun. It is due to a process that converts magnetic energy accumulated around the sunspot to heat and very high energy particles by the mechanism called magnetic reconnection. Solar flares emit intense X-rays due to their very high temperatures. The size of the energy of flares is classified in terms of the soft X-ray intensity. C-class flare, the smallest one, M-class flare, medium size, X-class flare is a very big one, with a factor of 10 difference in each step. For every 10 times increase in the energy of the flares, their occurrence rate decreases 1/10. We can imagine that the bigger the explosion on the sun, the more significant its effect on Earth would be. So we are naturally interested in the big flare rather than the small flares. How large can a solar flare be? To answer this question, we should first study the largest flare ever observed and its impact on Earth. Richard Carrington, an English amateur astronomer, observed the largest solar flares. A very bright aurora appeared the next day in Cuba, Bahamas, Jamaica, El Salvador, and Hawaii. These are quite unusual places to see an aurora. Telegraph system all over the Europe and North America failed. Telegraph pylons threw sparks, and telegraph papers spontaneously caught fire. The flare on 2012, July 23rd, observed by the NASA's stereo satellite, is supposed to be a super Carrington class, the very, very big flares. Though it occurred on the other side, invisible side of the sun from the Earth, if it hits the Earth, the estimated economic impact is estimated by NASA. That is to be larger than $2 trillion. We call flares many orders of magnitude larger than the largest solar flares ever observed, super flares. Then the question is, did super flare ever occur on the sun? And if the answer is yes, how large were they? A Nature paper recently reported a sudden increase of carbon-14 in the Japanese cedar trees. The increase took place suddenly in the year of 774 and 775. Since there is no apparent astrophysical phenomena like supernova explosions, a speculation is that this is due to a super flare much, much larger than the Carrington flare by a factor of 1,000. So if we are able to observe the 10,000 sun-like stars simultaneously, and if a super flare occurs every 10,000 years, we are able to observe a super flare every year in one of these 10,000 stars. This was indeed done by a Professor Shibata of the Kyoto University using the Kepler satellites, which can observe the thousands of stars simultaneously. Kepler serendipitously shows that the stars are prone to what we call super flares, which are shown there. The small sharp peak is a super flares. Occurrence of such event would be extremely rare, but with over 100,000 stars simultaneously observed by Kepler, many super flares have actually been detected. This particular example shows a super flare with a total energy 10 to the 36, 10,000 times larger than the largest solar flare. The periodic change in intensity seen here indicates that the star is covered with a gigantic star spot, as seen in above figure, a sunspot far larger than that we usually see on the sun. If the star spot is located on our side, the total amount of light coming from the star is slightly lower due to dark sunspot. Due to large star spot, such a huge star spot can carry magnetic energy far larger than that of the sun, producing a super flare. This is the energy size, the horizontal axis energy of the flare, and vertical axis is the occurrence rate. We see that the larger the flare, the less often it occurs, as indicated by red line. This is very similar to earthquake. Big earthquake is very rare. Big solar flare is very rare. The sun produces flares from very big one to the tiny burst called microflares. These range over 7 orders of magnitude. Interestingly, the histogram can be represented by a single line. Super flares observed by Kepler satellite are much larger than those solar flares, but they are on the same line extrapolated from the observed solar flare range. This implies they are driven by the same mechanism. This shows that even in the sun, a super flare 10,000 larger than the biggest observed solar flare can happen every 5,000 years. The Great East Japan earthquake that took place in 2011 resulted in 150,000 deaths and the meltdown of the Fukushima Daiichi nuclear plants. The earthquake of this magnitude happened every 5,000 years. It's the same rate, and the huge humanitarian and economic loss and widespread nuclear contamination indicates that we should be prepared for a catastrophe like this, even with this level of extremely low occurrence rate. So Kepler has seen 365 super flares with energy range 10 to the 33 to the 10 to the 36 ergs on 148 sun-like stars. This means that 10 to the 35 erg super flares, which are 1,000 times larger than the largest solar flare ever observed, occur once in 5,000 years in our sun. It's similar to that big earthquake occurred in Japan recently. Super flares cause strong ozone depletion and disaster for the civilization. 10 to the 37th erg super flare, once it happens, may cause much severe damage. A super flare, if it occurs in our sun or in stars that have habitable planet around them, may incur catastrophic biological and societal effects to any form or any life form or civilization emerging on this planet. So there are a lot of speculation here, but I think this may happen someday. M stars are very common in this universe. That is a small star. They are very lightweight and faint. Their habitable zone is therefore located much closer to the central star. Unfortunately, M-class stars are very active and produces flare with occurrence rate 100 times more than the sun-like stars. Super flares on M stars fatally radiate the surface of the orbiting habitable planets. So I am afraid if habitants of any emerging form in the M star system cannot survive. Sorry for them, but we recognize how lucky we are. So let me conclude. The increase and decrease of sunspot affect Earth's climate. There is no question about that. The sun's current state indicates that an upcoming Maunder minimum in 20 years, resulting in a global cooling of the Earth, though there may be the opposite possibility that the sun goes back to the normal states. We don't know yet. We also learned the real threat that ultra-rare super flare could affect our civilization and life on Earth. The situation is similar or more serious for exoplanets. Planets with magnetosphere are in a better position to have a life. Whether the life exists on exoplanet in the habitable zone, if other conditions are the same, may depend on the balance of the hazardous magnetic activity of the central star and the protective magnetic shield of the exoplanet. The research on the sun, its magnetic field, are so important to know if the life can form in another part of the universe. Thank you very much.